Hello everyone. Today we will understand some important theorems on composition of functions.
Yes, first of all, we will understand what is the meaning of composition of functions. If you have two functions f domain a to b, g b to c, then the composition of function f and g denoted by GOF is defined as a function GOF a to c given by GOF x equal to gfx for every x belongs to A. Now you can see that here A, the domain of f, will become the domain of GOF, and similarly range of G will become range of GOF. Now theorem f such that x to y, g such that y to z, and h such that z to s are functions, then HOGF equal to HOGOF. Here you can see there they have in NCERT they have given two theorems. We have to prove that both are uh, equal in we are doing first theorem number 1. In this they are saying prove HOGX GOF equal to HOGOF. It means that functions will also show the associativity property. We have to prove it. So how will you prove it? Now we start with this. We know that H composition G composition F is X is equal to H G O F X according to the definition. Now according to the definition we can say again H G F X in this way for all x belong to x. As you can see that this f is at the very close to the x, and according to this we are deciding the domain of the function, like g f g o f o g o f. The domain of this will be the domain of f, it means x. That's why we are saying for every x belongs to capital X set. Similarly we'll take this part, you can say this as now using property of definition we will prove two theorems of composition of functions. Theorem 1 says if f such that x to y, g such that y to z, and h such that z to s are functions, then HOGOF equal to HOGOF. You can see here it is a kind of associativity on the functions. We have to take all the three functions to show that these are associative also. For that we will take first LHS, left hand side part of function, HOGOF will take a number x which will definitely belong to f. Now we can say that h bracket g o f x, one more bracket, and now we'll apply g o f x in this, the property of definition. Like we can see here, h g f x. Now first of all, x g will be covered and then h will be covered. This is happening for all x belong to f. Now take right hand side part. See what will happen here. H O G O F X. Here we will take H O G F X first, and then we will take H O, this O, and F X, like this. You can see here this part and this part is same, so RHS is equal to LHS, hence proved. Now theorem 2. Theorem 2 says, let f such that x to y and g such that y to z be two invertible function. These are invertible function, and then GOF is also invertible with GOF whole inverse is equal to f inverse O G inverse. Now first of all, if these functions are invertible, then f inverse such that y to x and here g inverse z to y will also exist. By saying that these functions are invertible, these functions will definitely exist. Now if you have to prove that two functions are invertible, it is enough to say that for any two function, if I say like suppose f is a function O f inverse, if we are getting I identity function, or f inverse O f is also I, then we will say that both the functions are invertible of each other. Similarly here, if you will show that f inverse O G inverse composition G O F is equal to Ix, and G O F O F inverse O G inverse I Z. If you can show these two things, we will say that functions this will be true. Let's try. First of all, we are starting with the first part, f inverse O G inverse O G O F. We can say this f inverse O G inverse. I'm taking this G with this then I will be able to write this way by using theorem 1. Just consider this as one function, then this one function could be with this by using associative property from theorem 1. Now by using the property again, theorem 1 again, I can shift this brackets another side, like F inverse O G inverse O G O F again by theorem 1 again. Then G inverse G will be what? It will be I Y, because the domain, this domain of G is Y, so I Y will be here. Now why we are saying it? Because uh, G is invertible function, so here if both will exist, then we can say G O G inverse is I Z. We are using this property here. Now from this we can again say this F inverse O F O I Y will give you F inverse only. This whole will give you F inverse only, and from, if you will compose it this again, you'll be getting I F O F inverse will give you IX. So IX will come here. In place of this, IX will come. So this is identity function. We have got one. Similarly, you can show that if I'll reverse it, G O F O F inverse O G inverse, again by associative property we can say G O F O F inverse. I'm just changing the brackets. Now this whole, again changing the brackets, we'll get G O F inverse. This will again give you G O F inverse is I X O G inverse. Now again it will give you G O G inverse, and that is I Z. So from B you can say. So using A and B, you can say that G O F whole inverse is equals to F inverse O G inverse. By using this property, you can also say if you have three functions, suppose F, G and H, three functions are there, F O G O H whole inverse, you can say H inverse O G inverse O F inverse. This you can use as a property every time.